Okay, this is active filter design, lecture 29. In the last class, we understood the stability aspects of a common mode feedback loop, and we concluded that our fully differential transconductor that we have so far looks like this. Okay. I mean, these are just this is just one way of doing this. I could, in principle, keep the PMOS current sources fixed and make the tail current source 2I0 be the control source. Finally, you want the current, the common mode current that's being pushed by the PMOS sources to be exactly the same as the common mode current that's being pulled by the NMOS transistor. Is that clear? So, we also understood that this error amplifier is an appropriately compensated error, right? And in our example, what we said was that the common mode gain, or rather if I break the common mode loop, say here, and yank this up by delta V, okay, then if you didn't compensate, you basically have what do you call? You basically have two integrators in the loop. One integrator from this point to this point, another integrator from this point to back to here. Since you have two integrators in a loop, the closed loop dynamics, so the closed loop response as far as the common mode feedback loop is concerned only will have poles on the j omega axis, so it will be unstable. And to fix this, what we said was we could Miller compensate, recognizing that this is nothing but a two-stage op amp in disguise. One thing that we could do was do this. Okay, where we understood that this is actually a the simplest thing you could do for this is use a differential pair whose output is VCM detected minus VCM reference times some GM. Okay. Now, let me ask you a question. If VD was 0 and I injected a small current, two current sources I and I in this fashion, can you comment on the common mode voltage detected at the output of the detector? Qualitatively, can you comment on the output waveform there? Let's say I does this, right? So this is I of t. It starts at t equal to 0. This is a sudden jump in I. So what do you think will happen to VCM Let me call that VCM out. So what do you think will happen to pardon? So if you pump current into a node, what will be the tendency of the node potential? To increase, correct? So it probably does something like this. And then what happens? Feedback, the feedback loop has got a finite time constant. It doesn't, can't act instantaneously. So by the time the feedback loop, figures out that something is wrong and goes and corrects it, some time has elapsed. During that time, the output will tend to go up. So in fact, if I draw here the integrating capacitors, the ones shown here are the integrating capacitors. So if the feedback loop wasn't there at all, if I pump two currents, what will happen to the output common mode? It will increase like what? It will tend to go up like a ramp, okay? But soon enough the feedback loop starts to act, and eventually what is the common mode voltage? It will be Vref. Why? Or VCM ref? Because eventually if the common mode loop is stable, the current in the PMOS transistors is adjusted so as to make the sum of rather it is adjusted in a way that the total current being pushed into the node is exactly equal to the total current being pulled out of the node. So eventually the voltage must settle to VCM ref. Okay, this is just some example waveform I have drawn here. All that we are sure of is this ramp here. The slope of that ramp is very clean. It can be determined without any problem and ambiguity or any knowledge of the rest of the network. Why? It's simply, what is the rate at which the voltage rises? I by C. Okay. Now if the loop is very fast, what do you qualitatively think will happen to this waveform? What will happen to the initial slope? It will be the same, it's just that the feedback loop will kick in faster and do this. You understand? Okay? Alright? Now if this capacitance is made smaller and smaller, what do you think will happen to the slope of the ramp? As if those capacitors, the integrating capacitors are made smaller and smaller, this will become, the slope will become higher and higher, and eventually the slope will tend to, hey guys, slope is I by C, C is tending to 0, how will it, infinity, right? So if you put a step current into a node and you see that the voltage jumps up to infinity, what kind of impedance is there? If you didn't know anything about transistors and stuff like that, you pump in a step current into a node, the voltage slope is infinite. What does that mean? What kind of impedance is that? Yes, come on guys, if I put a step, okay, and I put a resistor, okay, as the slope keeps, okay, so if so a lot of people seem to think it's a resistor. So if this is the input, what will happen to the, if there's a resistor, a large resistor, how will it look like? It will be this step multiplied by the large resistor. It will never go to infinity, correct? So the fact that you put in a step and you're seeing an infinite change in the output voltage means that the impedance has to have an inductive component. Does that make sense? Okay. So in other words, if this capacitor wasn't around, the rest of the circuit in parallel with the capacitor must have an, C being 0 is the same as capacitor not being there. If the capacitor wasn't there, pushing a current into those two nodes means that the voltage will attempt to jump up to infinity, right, and then the negative feedback loop wakes up and then goes and fixes the gate of the PMOS transistors and brings it all back to VREF, correct? So if you want to model the impedance as far as the common mode signal is concerned, what do you think is a reasonable model given all these facts? So I have put in a step I, correct, and the change in the voltage is, you know, there is a capacitor here, correct, and what is the rest of the story? As C tends to 0, the slope goes to infinity, so there must be an inductor, okay, and at infinity, at t equal to infinity, what is the voltage across the current source? Yeah, but so incrementally the voltage must be 0, so basically an inductor and capacitor in parallel. Does make sense? Okay. No, the voltage will go to infinity, isn't it? If the slope goes to infinity, no. See, it cannot be a step increase because why? The feedback loop is still sleeping, right? So what is happening? This voltage is still, it doesn't know anything, correct? Wow, all that you have done is suddenly pushed in two currents. If these integrating capacitors were there, then that current would all go into the integrating capacitors and the output would ramp up, right? The steady state value of that ramp in principle is infinity, correct? Now as that capacitance becomes smaller and smaller, you see that the ramp becomes steeper and steeper and the steady state value is infinite. You understand? Even for an infinitesimally small step. Does it make sense? Okay. So this is a general principle, right? Whenever you have a negative feedback loop making a voltage source, you understand? Please note that as far as the common mode feedback loop is concerned, the equivalent network looks like this. This is nothing but a two-stage op amp. Okay. All right. And this is VCM ref. We saw this in the last class, and this is VCM out. Okay. Now all that we have done is said I'm going to apply a step current into the output. Okay. And we are saying that the output voltage, I mean, if there was a capacitance here, the output voltage would do something like this. If this capacitance wasn't there, then it would shoot up to infinity and then come down depending on, you know, how fast the feedback loop is working. Correct? Qualitatively, this is what is happening. Of course, one can go and do the maths and so on. But what I want to point out at this stage is that any amplifier which attempts to be a voltage source based on feedback principles, okay, I mean, what do I mean when I say a voltage source based on feedback principles? What is internally happening is that it is not really a great voltage source to begin with, okay, but it is monitoring the difference between the output voltage and the reference and doing whatever it takes to keep the output voltage the same as the reference, right? That's what this negative feedback loop is doing, correct? However, this feedback loop has a, I mean, in speaking very loosely, has a delay, right? So since the feedback loop is not fast enough, a sudden push of current into the output of the amplifier, right, which would in the case of an ideal voltage source, it would result in no step change in the output voltage. In fact, for an ideal voltage source, if you go and pump in a current, the output voltage will not change. However, this is a within quotes fake ideal source, right, where it's actually being fixed by feedback, but the feedback loop has got a finite speed. So, you pump in some current, suddenly the voltage rises, and then the feedback loop figures out that there's a difference between the reference and the output and goes and does whatever it takes to fix the output voltage. This takes time, right? But during that time, the output will jump up, and depending on the speed of the feedback loop will eventually come back to 0. Is this clear? So it means therefore that the output impedance of any feedback loop based voltage source must contain an inductive component. You understand? Simply by virtue of delay in the feedback loop or finite bandwidth of the loop.
In the open loop, it will have very high impedance, and then when you put in closed loop, it will be that impedance by 1 plus beta.
It's not entirely correct, but yeah, that's for those of you who've done, who have experience with loop gain and output impedance and the effect of loop gain on output impedance. Loosely speaking, the closed loop output impedance is nothing but the open loop output impedance divided by the loop gain. Okay. Those of you who not, if this argument doesn't make sense to you, don't worry about it. It's not important. For those of you who actually heard this stuff before, you can interpret this as the closed loop output impedance is open loop output impedance divided by the loop gain function. The loop gain is falling off as a function of frequency because of poles in the feedback loop, which means that 1 by loop gain must go up with frequency, right? And which basically means that the closed loop output impedance must increase with frequency, and any impedance which increases with frequency must consist of an inductive component. Is that clear? Okay. All right. So what do you think this inductance will depend on? If the value of this inductance, can you guess what it depends on? It depends on how fast the feedback loop is. If the feedback loop is very slow, then the inductance is very large, correct? If on the other hand the feedback loop is very, very fast, the inductance is very small. If the feedback loop is infinitely fast, the inductance is 0, because the loop will just hold the output voltage to VCM ref regardless of how much current you pump into the output. Is that clear? Okay. Now why am I discussing all this? It turns out that this is indeed a problem, as I'll show you. So as far as common mode signals are concerned, the equivalent of the fully differential so in other words, if I am interested in only common mode signals, that is something like this, then if I relate a change in the input common mode as far as common mode signals is concerned, how does this look like? What is there in the load? What is there here? We just discussed that looking up, it looks like that whole common mode feedback loop basically looks like an inductance. Okay, so all right, and this is what is this capacitance now? Integrating capacitance. Okay. All right. Okay, this is, I'm sorry, I missed something. Okay, I'm sorry, I missed something. Okay, so what I forgot to mention was all this. I mean, all this is true. One thing, another component that I forgot to mention, or rather I missed mentioning, is see, if I pump in a current like this, and this is all that there is to the common mode impedance, what do you think will be the output common mode response? It will be oscillating forever. The fact that it comes back means what? There must be damping. And where do you think in this loop? I mean, where is the damping happening and how is it happening? Assume transistors are all ideal with infinite RO. Where do you think damping is happening? I mean, because the feedback loop is as vague an answer as anything else. Why? Why because of CC? Can you give some more insight? It is because of CC, yes. Okay, wait. If CC wasn't around, what do you think will happen? Okay. Okay, sorry, let me rewind. Let me draw the common mode equivalent so that we don't get confused. This is the common mode equivalent. This is the common mode detector, right? And this is the error amp, which we all understand that it's a transconductor which is actually pumping current out, and this guy is the compensating capacitor. This is the common mode equivalent circuit, and what we are doing is pumping a current here and looking at the output voltage here. Okay, so this is CC. Without CC, what happens? We all agree that the poles are, there's a one parasitic pole there because of that capacitance. There's another parasitic pole here as far as the common mode loop is concerned due to the integrating capacitance. Okay. Now, without CC, what happens, why the loop is oscillating is because there's one integration from here to here. This is a transconductor. The error amplifier is basically a voltage controlled current source. So the input to the output of the error amplifier is an integration. From here to here, there is another integration, and the two of them are closed in a negative feedback loop. So we know that this oscillates. Okay. Now, and we also know that if we put CC, the loop is stable. Correct? So what does this mean? CC is what is is responsible for stabilizing the loop, which basically means that in some sense CC is what is responsible for damping this two integrator loop, right? If you had a damped loop, it means that you just can't have the equivalent model, just simply cannot be an L and a C in parallel. There must also be some resistor somewhere. Okay, either a resistor in series with the capacitor, which cannot be true because the capacitor is, this is C1, correct? So they must, if there is damping somewhere, it must be either in series with this or in series with the inductor or parallel with the inductor. Why can't it be in series with the inductor? A resistor in series with the inductor will also damp a second order network, isn't it? It cannot be in series with the resistor, with the inductor, because we know that at t equal to infinity the output common mode is the same as the initial common mode. So the incremental change in the common mode voltage is 0. Correct? So there cannot be a resistor in series with the inductor. So there must be a resistor in parallel with the inductor. This is what must be happening. Okay, we try to understand why, how this happens. Okay, see, please note that it's actually quite straightforward to go and sit and write the maths and get the expression. What I am trying to do is to derive intuition for why this equivalent circuit makes sense, and why CC can be interpreted as introducing a parallel net resistive loss in this second order network. So if I yank this suddenly, if I yank this voltage suddenly, all right, what do you think are the components of current that flow into the that flow out of this voltage source? Let's say I put a incremental voltage source here and yank this up like this. Okay, what all currents flow out of this guy? There's one component flowing through C1, and that, what kind of component is that? If I apply a step change in voltage across a capacitor, what is the current that flows through the capacitor? It is it's an impulsive current. Okay, so that also flows through this C1 in the equivalent circuit. So that is accounted for, right? What other, where else can other currents flow? There cannot be a current flow like this, correct? Because it's a voltage controlled voltage source. There cannot be a current flow like this, because it's a current source there. Okay, the only other component of current is the one that's being pumped by the PMOS transistor, right? The PMOS transistor's current can change only when its gate source voltage can change. The source voltage is fixed. So the only fellow responsible for change in the PMOS drain current is simply the change in the potential at the gate. Correct? Now, if CC wasn't around and only CP was there, then a change in the potential here will cause a change in the potential there. Correct? Because that's a unity gain buffer, which means what will happen to this guy, the error amplifier? What is he doing? He is pushing a current into CP. But what can you say about the voltage across the capacitor? If you push a step current into a capacitor, what will happen? It will ramp up. In other words, at t equal to 0, the voltage across the capacitor will remain put at, incrementally at 0, or will remain at the same value as before, which means that instantaneously the current in the PMOS transistor cannot change. Correct? Alright, which means that the output voltage, which basically means that all the current if CC wasn't there, all the current the instantaneous current at t equal to 0 is all flowing through the capacitor, and that makes sense, because if no current flows, if CC wasn't around, then this loop looks like this. All the instantaneous current flows through C1. An inductor's current cannot be changed instantaneously, correct? So no current flows through the inductor, and it's all self-consistent. Now, the moment you put, it is the gyrator. It is two. In the time domain, on the left side, on the positive terminal of the error amplifier, there is a step. The voltage here is a ramp. Okay, what does that mean? The input is a step and the output is a ramp. It's an integration. Correct? Now, this step will cause this voltage to go how? Here it is held, but if somehow there was a step at this node, and how does this two integrator loop work? you assume there is some noise like step before, it results in a ramp. The ramp will get integrated and result in a parabola that's being fed back, and then that's the starting part of the oscillation. Okay, all right. Now, once Cc is put, okay, there is another mechanism that is responsible for changing the potential of the gate of the PMOS transistor. And what is that? There is direct path through Cc, and what will be the change in the voltage at the gate due to a change in the voltage here? This is delta V. This is also delta V. If this goes up by delta V, what happens to this potential? Cc by Cc plus Cp times delta V, which means that if the gate goes up, what must be happening? Current is drawn in which direction? Incremental current flows up or down? Must flow up. How much is that current? It is this current must be GMP times delta V times Cc by Cc plus Cp. Okay, so and this will be a step current because delta V is a step. So if you put in a step voltage and a step current flows out, what does that mean? It's a resistor, and what is the value of that resistor? One plus Cp by Cc times 1 over. You understand? Okay, I apologize for the goof up. I forgot about Cc completely the last time around. So, as far as common mode signals is concerned, the equivalent network, if one were simply to quantify the change in the output common mode, if I draw the incremental equivalent, if I quantified the change in the output common mode due to a change in the input common mode, this is how it would look like. You understand? Why? What has happened to the tail current source? Why is it open? Because the incremental equivalent. Okay. So, and this basically goes into the output, into a load network, which is an RLC network. Is this clear? Please note that as we have drawn it right now, if I change the input common mode by some amount, okay, if I change this guy by a little bit, can you guess what will be the change in the common mode here? This is an open circuit, so incremental current in the drain due to a change in the common mode is 0, correct? So in principle there should be no change in the output common mode voltage. This is exactly the same as the differential pair argument, right? In a differential pair with a tail current source, if the common mode changes, what do you think will happen to the output common mode? Doesn't change because of the common mode rejection ratio of the differential pair. Okay, so please note that you must all be very, very thorough with the differential pair, right? It's perhaps the most important circuit. It's governing all our lives because everything in the world is a differential pair, right? Okay, every analog thing is simply differential pairs in various forms, okay, and you should be very thorough with the operation of the differential pair. Okay. So technically, it seems as if we are safe, because even though there is an LCR network at the top, the amount of current exciting the LCR network is 0 because of the infinite output impedance of the current source. In practice, however, what are all the non-idealities you can expect with the current source? Finite output impedance, but more importantly, there is also going to be parasitic capacitance here. So, this finite output impedance as well as some parasitic capacitance, which you cannot avoid. Okay. So, even though you think that the current is small, in fact, or current is 0, there is in fact some current because of the parasitic impedance at the source node. This is, please note, the common mode impedance at the source node, right. And let me reiterate again, at the risk of sounding boring, okay, this incremental circuit is used or should be used to relate what to what? Changes in the input common mode voltage to changes in the output common mode voltage. Okay. Why I am emphasizing this so much will be apparent the moment you take a look at a differential pair. So, this at a gyrator, this is the schematic of a gyrator, single-ended equivalent schematic, correct. What kind of feedback is there for different for signals? I mean, this is clearly a feedback loop, right. So, if I break the loop and go around it, what is the sign of the feedback? If I break this here, yank this up, what happens to this voltage? Goes down, okay. If this goes down, this voltage goes down, what happens to this voltage? Goes down. So, what is the sign of the negative feedback loop? It's a negative feedback. You understand? Okay. All right. And in steady state, the voltage here must be 0. Correct? Okay. Now, let's, if the transconductors are all fully differential, how do you form a gyrator? This is the first transconductor. Okay, where the output current difference is proportional to the difference in the input voltages. Okay, and you take another gyrator which is also fully differential, which basically is supposed to, what is the job of the second voltage controlled current source? I mean, how would I hook these two guys up? Now you have two fully differential transconductors. How would I hook them up to make a gyrator? What should I do? Okay, this is a single-ended gyrator, folks. Okay. How, I mean, all I'm asking you to do is figure out, help me figure out how I'll arrange. Now I have a differential input current, voltage controlled current source, two of them. In the single-ended schematic, the output of the first transconductor is being sensed by the input of the second transconductor. So, in the fully differential schematic, the differential voltage at the output of the first transconductor must be sensed by the differential input of the second transconductor. So, what I would do, okay. Alright. And now what should I do? This minus must go to plus to minus. Oh, sorry. Yes, that's correct. Right? There must be an inversion either in the first transconductor or the second transconductor. This is a schematic of the fully differential gyrator. Okay? And where must you put the integrating capacitances? One capacitor here, another capacitor here, another capacitor here, another capacitor. Pardon? Oh, sorry. Yes, sorry. Yes? Yeah, I'll come to that. Okay? Does it make sense? One inversion is all that matters. It doesn't matter where you. Okay? Alright? Now, all that I want to emphasize is that if I break this loop and apply a differential input and trace what happens to the difference as you go around the loop, what would you expect for the sense of the feedback? Negative feedback. Is that clear? Okay. Now, let's see what happens to the. Please note that when I draw this animal here, what does it mean? What does it imply? Internally, what is there? There's the differential pair which is converting the input differential voltage into a differential current, and there are those PMOS current sources, and there is the common mode feedback loop which is sensing the output of the common mode output and tweaking the gate of the PMOS transistor such that the output common mode is held to VCM ref. Okay, all that is implied when I draw that triangle with that trapezium with two input voltages and two output currents. That clear? Now when we put two of them together, that means that how many common mode feedback loops are there? There are two common mode feedback loops. One loop is trying hard to maintain the common mode voltage here equal to VCM ref. Another common mode feedback loop is holding the common mode there at VCM ref. Okay? And these transconductors have been connected in some fashion, in this particular fashion, because we are trying to realize a gyrator, and as far as we are concerned, we only really care about the differential signals, correct? As long as the common mode voltage is held at VCM ref, right? I mean, we are not attempting to do anything with the common mode feedback loop. Correct. As long as each common mode voltage is held properly, we are happy. Right. This loop is only set up at least with the intent of keeping, realizing a gyrator for differential mode signals. Is that clear? Okay. Now let's see what happens for common mode signals. For common mode signals, can I reduce this to something? What should I do if I want to examine what happens when I put these two things in a gyrator? What happens to the common mode signals is a valid question. So the inputs are the same as far as the common mode is concerned. You replace each gyrator with its common mode equivalent circuit. And what is that common mode equivalent circuit? This is the equivalent common mode for common mode signals, correct? So this is the common mode equivalent to one gyrator. this is the second gyrator, correct? And as far as common mode signals are concerned, what is happening to the two transconductors? The output common mode signal of the first transconductor is, please note the following, yeah, with as far as with appropriate signs. This is one transconductor, this is the other one. Okay, please note that the output common mode here is nothing but the input common mode for the second guy. So what should I do in this picture? Very nice. Okay. All right. And now what happens to the other one? No, look carefully. What happens? The output common mode of this transconductor is nothing but the input common mode for the other, correct? You understand? So what should happen? Output of the second one I'm just going to flip this just to make this look nice and symmetric. You understand? Why should there be a -1? Please note that this only relates common mode signals, correct? So far as common mode equivalents are concerned, both these nodes are the same potential, correct? So in other words, if I yank this common mode up, okay, what do you think will happen to the output common mode voltage? Okay, let's see what happens. If I yank this up, okay, what do you think will tend to happen to this output voltage? It will tend to come down, okay. If this comes down, what will tend to happen to the output common mode? Let's say I break the loop here, break this thing here, it will increase. So what kind of feedback is this? Both of them have the same sign, right? Okay, and one output is the input of the other. The second out, both of them are feeding on each other, correct? So even though there is negative feedback for differential signals in the gyrator, there is positive feedback for common mode signals, okay? And for those of you who've seen this before, right? Can somebody recognize this? It's nothing but an LC oscillator. You can think about it in this way. These, if these connections weren't around, these are nothing but two RLC networks, correct? Now, if I did this, let's assume that this voltage goes up by some delta V1 and this goes down by delta V1, correct? Okay, so if that goes up by delta V1, what is this current? Some GM effective, which depends on R, CP and all that stuff. We are trying to do the math, but some GM effective times delta V1 is the current there, correct? What is the current here? It is GM effective times delta V1 going in the opposite direction. Now as far as this node is concerned, let's see what's happening. I'm increasing it by delta V1 and current is coming back at me, and that current is some GM effective times delta V1. So equivalently, what is the impedance? It's negative impedance. It's 1 by GM effective minus 1 by GM effective is the negative impedance, because normally what do you think of an impedance? If I yank the voltage by delta V, current goes out. Delta V by R is the current going out. If current actually pops back in, we know that the impedance is negative. Correct? So as far as this network is concerned, it looks like a negative resistance. So you have an RLC network which is lossy because of the R, but now in parallel with it you have a negative resistance. So if the net resistance is negative, what do you think will happen? The poles will be in the right half S plane and this will oscillate. But what kind of oscillations are these? It's going oscillation, but for what kind, what mode of signal is this? For common mode. Please note that this equivalent circuit is only for common mode signals. So it is, when I say you will see oscillations, you will see common mode oscillations, because even though a single transconductor is stable and nice because you've gone and designed the phase margin, blah blah blah, all very well, right? The moment you make two transconductors and put them as a gyrator, there is a common mode positive feedback loop formed because of the way the transconductors are connected. And why did we connect the transconductors that way? Because we were interested in realizing a gyrator for differential signals, right? And each transconductor has got a common mode feedback loop stabilizing its output, but when unfortunately these two transconductors are put together, there is a positive feedback loop for common mode signals. Does it make sense? So it's a very common thing that happens is that you design the transconductor, and think everything is fine, and then you put all of them together and suddenly you find that your whole filter is oscillating, right? And the reason for that is that this common mode feedback, common mode oscillations can occur if the common mode feedback loop is not, strong enough. And what do I mean by strong? If it's oscillating, what does it mean? That means the negative resistance is much too negative, right? Alright, or the net current being pumped by the negative resistance is much larger in magnitude than the net current being pumped by being drawn out by the positive resistance, right? And which is the positive resistance? R. Okay. So if you have to fix the stability, you have to reduce R or increase R? If you want to damp the tank even more, if you increase R, what happens to the poles? Q increases. That means it's more damped or less damped? Less damped. So if you want it to be stable, you want the damping factor to be as large as possible, which means that you must reduce R, because this is a shunt RLC network. Is that clear? Okay. So in this diagram, what does that boil down to? You have to increase CC.
Essentially, this problem came about because whereas flipping works for differential, flipping doesn't.
We're not really flipping. As far as the common mode is concerned, there is no flipping at all. You understand? Okay. Is this clear? So it's not just enough. The bottom line is that it is not just sufficient to design a transconductor and make sure that its output common mode is stable with whatever phase margin you want. It is quite likely that it's quite likely that when you put two transconductors in a loop to form a gyrator for differential signals, the the positive feedback loop, which is automatically formed for common mode signals, can make the gyrator unstable even though the individual units are stable. Right? You understand? Okay? And the fix for that is basically, there were several possibilities. One is to reduce R. Okay? I mean, basically you have to reduce the quality factor. Okay? Another way is to keep R the same and reduce L. Correct? Because the quality factor is proportional to 1 by R, I mean whatever, R divided by, I'm sorry, sorry, that's, reducing L does make sense, but I'll tell you why. Yeah, well, I guess it's already, I mean, if I start that discussion, it will go on for another 15 minutes. So, I will continue about this in the next class. By the way, I wish to make an announcement. The next tutorial has been put up, right? It is due on March 31st. It's a somewhat longish tutorial, right? Or a problem set rather. Please start working on it now. And you know, if you start the day before, I'll assure you that you will not finish it. Okay? All right.